Hi everyone, this is Mr. Lee. In this video, I'm just going to go over our lab. And in the lab, I asked all of you to just sketch down the graphs that you got with your data so that you have something as a reference. Um, Now, if you don't have all the necessary graphs, feel free to just copy my theoretical data down as part of your notes. But for this part of the video, you don't have to really jot down anything, only the big main ideas, and I'll tell you exactly when that will begin. So if we were to begin, I have here three sets of graphs, and these three sets of graphs are theoretical data that I just made up, just so that we have something nice and clean to do. So the first row is the low incline, and you can see here on your screen that the first graph on the left is a position time graph, and that says x is equal to 25t squared. Okay, the middle one is a position versus time squared graph, and that says x is equal to 25t squared. That's the formula. And the one on the far right, this is the velocity time graph, and this is v is equal to 50t. All right, and then down here, I have data for a high incline, and my high incline, I have formula of x is equal to 100t squared. My position versus time squared graph, I have x is equal to 100t squared, and my velocity time graph, I have 200t. So if you have your data in front of you, you can see, how well or how accurately you all plotted the points by seeing, okay, do my lines of best fits, do my formulas follow this trend? All right, I'm going to go over the trend with you in a little bit. So I created a quick little table with all the formulas so that you can see the type of graph that the formula came from. So we can see here that the low incline, there's a couple of things that I want to point out. One, it starts off with a 25, whatever that value represents, and we'll go over exactly what that 25 represents, and this 100, right? So we can see as we go from a low incline to a high incline, this number does in fact get bigger. And that's a clue to really let you know what this number in front of the t-square represents. All right, the next set of clues we see is that this 25 and this 100, it's the same exact value, okay? And this was the slope for the position time squared graph, meaning that hopefully at least one person in your group got a linear line, okay? What this slope represents was our 25 for the top one, and this slope here was the 100 for the high incline one, okay? So we see that the 25 is shared versus the two graphs, even though it has a different shape, and the 100 here is shared between the two graphs, even though it had a different shape. And we have the last column. So the last column still follows the trend, right? The low one has a lower value overall, and the high one has a higher value overall. So 50 versus 200. And the other thing I want to point out is that this 50 here is exactly double this 25, and this 200 here is exactly double this 100 there. Now, this is because I made theoretical data, meaning my data was exactly what I wanted to look like. And so yours might not be exactly double, but like maybe if you rounded the number, it could be interpreted as double the value. And if you did that, that's fantastic. If not, that is a-okay. All right. So now let's go over what the 50 and the 25 and the 200 and the 100 represent in terms of objects that are speeding up. So the first thing I want to go over is the velocity time graphs. Okay. So the velocity time graphs that I got here, okay, it was a linear line. So if I were to go over the definition of the linear formula, okay, we would get something like this. So this is where your notes begin. So for a velocity time graph, our formula was y is equal to mx plus b. Now the website does use different values. They use ax plus b, but you'll see mx plus b represented in your math class. Now, with that being said, we're not a math class, we're a physics class. So let's rewrite what those variables represent. So our y-axis was actually velocity, and we're trying to figure out what the slope represents. Okay, we don't know what the slope represents just yet. and then we have the x-axis, which represents time. And for our perfect data, our plus b was 0. Okay, and I'm going to actually keep that there. Usually I ignore the zeros in our formula, but this time that 0 actually represents something. So I'm going to leave that there. Now, slope is a ratio, okay? And in this case, the ratio that our graph gives us is that for every velocity, we have a little bit of time. And this gives us our slope. So if we were to look at the very definition of slope, what this really tells us is that for every change in time, right? So what this means is that as time moves forward ever so slightly, like for example, if we got 0.00001 second, right? So if we have a slight change in time, we'll have a change in velocity. Now, with this, this here is one of the most important definitions for our physics class. What exactly is the change in velocity? Change in velocity is how much our velocity changes for speeding up or slowing down. Okay? Now, the reason why I want to emphasize this, and the reason why I'm saying this is a very important idea, is because the common populace uses this term incorrectly a lot of the times. And this definition here is the definition for the variable acceleration. Okay? The definition of acceleration is how much your velocity is changing by. So that is either a speeding up or a slowing down. And so the formula becomes acceleration, which is a, is equal to v over t, but because we're looking at the change, it'll be delta v over delta t. All right, and the units for velocity is meters per second over the units for seconds, or for time is just seconds. Okay, so it's meters per second per second. Now, this is the longer way of writing it, and by definition, that is the better definition for the units, but sometimes you'll see it written as meters per second squared. So let me go over why I like this definition for acceleration. Now remember, acceleration is how much your velocity is changing by. So the important thing is that it shows you that there's a ratio. You're comparing two variables against each other. So for example, if you have a acceleration of, let's say, 3 meters per second, okay? Now remember, in the denominator, technically, there's a number 1, okay? So if we have an object that has an acceleration of 3 meters per second, this right here, in my opinion, tells you a lot more than if we were to say 3 meters per second squared. So the example is, if you have an object with an initial velocity of 0, so we are starting from rest, right? And we have an acceleration of 3 meters per second every second. What that tells us is that at time 0, our velocity is 0. But every time our time changes per second, our velocity has to change by 3. So after 1 second has passed, because our ratio is 3 meters every 1 second, our velocity has to change by a factor of, or by a total amount of 3. So at 1 second, our velocity therefore becomes 3 meters per second. All right, so after 2 seconds have passed, that means that from here to here, a total of 1 second has passed. So for every 1 second that passes, our velocity is adjusted by 3 meters per second. So our velocity now becomes 6 meters per second. And so here, what we're seeing is that the object is speeding up. So here we're seeing that the object is speeding up. Now, if we were to do that, helps us go over the definition of what this slope represents. So if we go back to our table here, we can see that the low incline had a slope of 50, and the high incline had a slope of 200. So what this shows us is that the high incline made it so that the ball sped up by a higher amount with every passing second, and the low incline here, it sped up with a lower amount of velocity for every passing second. Okay, so that leads us to the next two formulas here, right? So we have x is equal to 25t squared, and x is equal to 100t squared, right? So if we take a look at it, we can see that in both instances, the values is exactly 1/2 of the velocity time slope. So that will lead us into our next formula. So the formula is, if we were to come up with a formula for the position time squared, is that your final position is equal to, right, whatever this numerical value represents, which we said it was 1/2 of the slope. And remember, the slope for a velocity time graph is the acceleration, okay, times t squared, right? Now, this is just only one part of the formula. The other parts of the formula, so this is the part of the formula that we got from our lab. The other part of the formula actually comes from the line of best fit quadratic formula. And so the mathematical formula is y is equal to ax squared plus bx plus c, right? And so if we were to do a one-to-one comparison, we said the y-axis represents our position, in this case our final position, and our a value, remember, this was exactly 1/2 of the slope for the velocity time graph. So this is 1/2 of the acceleration. Now, just so you know, this is like the capital letter A, and let's say this is the capital letter B, and this is the capital letter C. So this lowercase a is the acceleration. Okay, so that's how much the object is speeding up, slowing down by. T squared plus this b right here. Okay, this is actually something from the Buggy Lab that we did. So just a little side note, when we did the Buggy Lab, our formula was x is equal to velocity times time, right? And so we had this velocity variable in front of this just time variable, and we see here this x represents time. So that means that this b represents the velocity. And in our case, this will represent our initial velocity. And we have this plus c, and that plus c represents our initial starting point. So that right there is the formula that we can use to describe an object that is either speeding up or slowing down. Or more specifically, this is the formula for accelerated motion. Okay, so that's one of them. The other formula that we found for accelerated motion was from before, but because we're here, let's also copy this down. The other formula is v over t, or the change in velocity over the change in time, which is equal to acceleration. But if I were to break this down even more, I would write vf minus vo over time is equal to a. So if I rearrange the formula in a way that you'll see on your formula sheet, it would look something like this. Vf minus vo equals a times t, and then we have final velocity is equal to initial velocity plus acceleration times time, right? So we have, this is our next formula right here for accelerated motion. So we have two formulas for accelerated motion. Now that we have our two major formulas, right? We have xf is equal to 1/2 at squared plus v initial t plus xo, and we have v is equal to v initial plus at. Now we can go over the big main idea of graphical analysis. Okay, so the idea here is y I had you create a position times squared graph in the first place. So this idea here is what we call linearization. Okay, linearization simply means that you take a line that is not a straight line and you adjust the data so that you still have the same relationship. Okay, and in this case, the relationship that we saw was how much the object sped up by, but it's in a line form. And the reason why we like a line form is because it's a clean ratio, right? For every one thing, another thing happens. So to give you a recap, we linearized our data, and the relationship we were looking for was actually this number here, this 25, this 100, and this 100. So based on whatever you got. So the ability to linearize, now if you remember, this graph here, we got something that looked like this, okay? Understanding what this curve shape is pretty hard for like our minds to just quickly pick up on. But if we were to look at a straight line like this, the ability to find the slope of this line is a lot easier than finding that a value for a curved line. So the whole purpose of linearization is for us to be able to find the slope a lot easier. But the important thing is that the slope is the end relationship that we're looking for. And for us here, the end relationship for that slope represents our acceleration. Now, to be specific, this acceleration was exactly a half of the actual acceleration based on what we discussed